Hello, I'm Andy from Space Oddities. Next to black holes, neutron stars are probably the most bizarre objects in the universe. First predicted in 1934 by astronomers Walter Baade and Fritz Zwicky, it was not until 1967 that they were first actually observed by Jocelyn Bell, now Dame Jocelyn Bell Burnell, then a research student at the University of Cambridge. In these Weird Wonders videos, we're going to enter the weird, wonderful world of neutron stars, where matter, magnetism and gravity behave in ways we can scarcely comprehend. In this first episode of the series, I'll be looking at how neutron stars form. Go out under a starry sky in winter or early spring, and you cannot fail to notice the constellation of Orion, one of the most recognisable in the heavens. At Orion's left shoulder there is a bright star with an obvious orange colour. This is Betelgeuse, a red supergiant star some 600 light years away. Betelgeuse is a truly gigantic star, shown here compared in size to some other giant stars and our Sun, which as you can see is tiny by comparison. Betelgeuse is so vast in size that, despite its distance, astronomers have been able to capture an image of its surface, which is not possible with more than just a few stars. Most stars, even in the largest telescopes, appear as mere points of light. The red giant phase of a star occurs when it nears the end of its life, starts to run out of hydrogen and puffs up into something monstrous and bloated. This is in fact the fate of our Sun. In 4 or 5 billion years' time, the Sun will be nearing the end of its life and will have expanded to become a red giant star, swallowing Mercury, Venus and very possibly the Earth as well. This picture shows what the Sun may look like from the surface of the Earth when our star becomes a red giant. After millions of years as a red giant, radiation pressure from the core of the Sun will cease and our star will shrink to become a slowly cooling white dwarf star, finally ending its life a cold, dark cinder. But what of stars larger than the Sun? What happens to them? Stars with more than about 8 times the mass of the Sun do not become white dwarfs. Instead, they end the red giant stage of their lives by blowing themselves apart in what's called a Type II supernova explosion, a detonation of such unimaginable magnitude that in just a few seconds the dying star may release more energy than our Sun will emit during its entire 10 billion year life. In this type of supernova, the star blows away its outer layers, leaving just the core of the star behind. Immediately after the supernova explosion, there is no longer any outward radiation pressure from the core of the star. Consequently, in the sudden absence of any resistance, gravity is able to suddenly and violently compress the core, reducing its size from thousands of miles in diameter to just a mere handful of miles across. This process may happen within a few seconds. The atoms in the core are squeezed closer and closer together, so much so that electrons orbiting the atoms are unable to sustain their orbits and crash inwards to the atomic nucleus, combining with the protons to form neutrons as a bizarre ultra-dense element called neutronium. A neutron star is born, which consists largely of neutronium. It possesses between 1 and 3 times the mass of the Sun, packed into a sphere perhaps just 10 miles across. You may be familiar with the periodic table of elements, where each element has an atomic number representing the number of protons present in its nucleus. Hydrogen, for example, is atomic number 1 as it has just 1 proton. Neutronium is numbered 0 in the periodic table because it does not have any protons. They have all been converted to neutrons. At this point, gravity cannot compress the new neutron star any further, as something called neutron degeneracy pressure pushes back against gravity, preventing the neutron star from shrinking further under gravity's relentless assault. The neutron star is now in finely balanced equilibrium. However, if the star was originally 5 times or more the mass of the Sun, not even neutron degeneracy pressure can exert sufficient force to stop collapse of the core altogether. Gravity wins the battle by compressing the core to a mere point, and a black hole is born. Therefore, whether the result of a supernova explosion is a neutron star or a black hole depends purely on the mass of the star. Neutron stars are bizarre objects indeed. Here is one shown for size comparison with Manhattan. Because up to 3 times the mass of the Sun is packed inside this small sphere, its density is almost incomprehensible. 1 teaspoonful of neutronium would weigh 4 billion tons. Because of its huge mass packed into a small area, the gravitational field of a neutron star is perhaps 1,000 billion times stronger than the Earth's. This intense gravity means nothing taller than a millimetre or so can exist on the surface of a neutron star. Anything taller would be immediately crushed by gravity. A neutron star is therefore a perfect sphere. Astronomers sometimes observe violent radiation outbursts on neutron stars which are thought to be starquakes, where the surface might slip by a couple of millimetres. This is enough to generate huge amounts of energy. The incredible gravity also means that if you were to drop a ball from a height of 1 metre onto the surface of an average 12-kilometre diameter neutron star, by the time the ball hits the surface it will be travelling at 1.4 million metres per second or 3.1 million miles per hour. And what of the interior of the neutron star? It must be said that astrophysicists are unsure about what exactly a neutron star looks like on the inside. As we cannot crack one open, we have to be guided by the physics alone, which suggests that the interior is made up of extremely exotic materials which do not exist on the Earth and which cannot be reproduced in a laboratory because of the extreme pressures and forces present. Here's a diagram from NASA showing the possible composition of a neutron star, but we cannot test this model through observations. The starquakes I mentioned earlier might give us an idea in the future of what's going on inside a neutron star, but short of travelling to one and making close-up observations, there's no way to investigate what these bizarre beasts in the cosmic zoo are hiding beneath their surfaces. As the closest neutron star is 170 light years away, or 1020 trillion miles, we won't be travelling to it in the foreseeable future. Well, that's it for the first part in this series of videos about neutron stars. Next time I'll be looking at pulsars, those rapidly rotating neutron stars which fire huge beams of radio energy from their poles like a celestial lighthouse. I do hope you enjoyed this video, and if you have any questions or observations, please don't hesitate to post them in the comments. We hope you can join us, the Space Oddities, on Mondays here on this channel at 8 PM UK time for astronomy news, chat and discussion from our resident panel of experts. We also hope that you'll subscribe to our channel, like our videos and tell all your friends, co-workers and families about us. Well, from me, Andy, until next time, goodbye.